Hi everyone, welcome to my virtual presentation. My name is Daniel Aguilar Marciac. I'm a PhD candidate at the University of Colorado Boulder. This is work that I did during my internship at the Mitsubishi Electric Research Laboratory in Cambridge, Massachusetts, with Stefano Di Cairano and Avishai Weiss. And so today I'll be talking about abort-safe spacecraft rendezvous in case of partial thrust failure. Rendezvous is important for several reasons. Let's define what it really is first. It's when you aim to drive a controlled chaser spacecraft to remain near and perhaps dock with a typically uncontrolled target body. It's important for several reasons. For human exploration, we've already seen SpaceX do this recently with their Crew Dragon capsule in the ISS, as seen or depicted here on the top right. For spacecraft servicing and maintenance, we expect that these kinds of services are going to be increasingly offered in the future to extend the lifetime of expensive satellites. This was also demonstrated recently by the Northrop Grumman Mission Extension Vehicle. And lastly, if we want to understand the formation of our solar system better or extract science, we can do this by performing rendezvous with space probes and asteroids of interest like O-REX and the asteroid Bennu shown here on the bottom right. The challenge really lies in automating this process in a way that safety is integral in the approach. So here we describe the rendezvous geometry between a chaser and a target spacecraft. Under the two-body assumption, we have an inertial frame centered at the central body, and with a target orbiting about it. We can use a target fixed frame called the Hill frame that points towards the target at all times. Here, I hat theta represents the velocity direction approximately, and I hat h represents the angular momentum direction of the orbit. So using this frame, we can consider the relative motion of the chaser as seen by the target body. Here we also show the chaser's inertial orbit, also under the two-body assumption. The relative position is given by the vector rho, and generally speaking, we are interested in driving this relative position vector to 0. In this work, we want to do so in a way that is inherently safe. With regards to safe spacecraft rendezvous, the goal is to achieve successful rendezvous while minimizing some performance metric and satisfying safety constraints. The performance metric may be given by control usage or fuel consumption, for example. The safety we're concerned with here has to do with partial loss of thrusters. In particular, we want to ensure that the chaser is at a state where at least a single powered abort maneuver would exist. So the high-level goal then is to maintain what we call abort safety relative to a polytope that closely approximates the target geometry. This is shown by the rectangle below. Here's an example of an unsafe initial condition. Since no abort maneuver exists, the chaser would not be able to avoid collision with the target. Some in the field may say that the chaser here has entered the target's capture set. Whereas here's an example of a safe initial condition, as an abort maneuver allows for the chaser to not collide with the target body. Most approaches don't typically consider safety after a failure. Traditionally, collision avoidance maneuvers are designed a priori, before flight, and they're engaged at certain checkpoints or if the chaser diverges significantly from the nominal reference trajectory. Others have used reactive collision avoidance policies or standard collision avoidance constraints with modern motion planning tools. The most related research was done by Breger, which uses an MPC controller that simultaneously solves for an abort sequence at every state in the prediction horizon. This work also considers viable thruster failure modes, as we do. Solving for the abort sequence results in a larger optimization. Also, the initial condition is assumed to be safe, and as such, there are no formal guarantees per se. Our approach generalizes this and is a bit different. Offline, we characterize the unsafe state space using reachability theory. Then online, we attempt to stay outside of the unsafe region by convexification of the constraints. This in turn results in a smaller online MPC optimization problem. In this illustration, we show the unsafe region around the target. Its complement is naturally the set of states for which aborts exist. As before, if the initial condition is unsafe, no feasible abort maneuver exists. If the initial condition is outside of this unsafe region, a feasible abort maneuver will exist. If passive abort maneuvers exist, that is, no control is required to avoid entering the terminal polytope, then the initial condition is said to be passively safe. We studied and published a paper on this topic in ACC 2020. The work in this paper generalizes those results. We desire to be safe with respect to a partial loss of thrust, which can happen if we have propulsion system or thruster failures. On the right, we see the assumed spacecraft model with thrusters on each corner of the chaser's body, which is actually a pretty realistic configuration in practice. And if we hypothesize particular thruster failure scenarios, we can construct admissible control sets for each failure mode by taking Minkowski sums of the individual thruster sets. Since each thruster's available force is modeled by a line segment from 0 to some maximum thrust, the resulting control sets are also going to be polytopic. We see a few examples of these on the bottom right. On the top left is the nominal control polytope, and on the bottom right is a case where a single thruster is functional, hence it's a line segment. Now, given a failure mode or admissible control set, we can obtain the sets of all initial states that end up in a terminal set, no matter the control used, using a robust formulation, as we can see in the equations here. And these sets then represent the set of states for which no abort maneuver exists in some number of steps backwards in time, and hence the terminal polytope would not be avoided no matter the admissible controls used. Here, we use the robust backwards reachable sets, but have replaced the disturbance set with the control set. As such, you can see that the sets are constructed with the for all controls as opposed to the for all disturbance argument. Also, if the control set is simply the origin or zero vector, we recover the passively unsafe sets. So for a given control set and a final time, we can compute the set of all states that enter the terminal set, no matter the control used in, let's say, n steps or less. And since Abort-Safety is concerned with the final rendezvous phase, the linearized dynamics of the system around this area are extremely accurate. So we can use this generic LTV description here. This is useful because that means that if our terminal set is polytopic, as we see here by the equation below, every RBRS itself is going to be polytopic. And we can compute the RBRS for a given final time and control set recursively, as you can see on the right, by taking this Pontryagin difference. And then if we take the union across all of these backward time steps, we obtain the set of all states that enter the terminal set for all controls in n steps or less. And naturally, this union need not be convex. In fact, it's likely non-convex, and we'll get into that, what its implications later. So to be safe with respect to several final times or target positions, we need to take the union of the RBRSI across an orbital arc of interest. So here we show a target in an elliptical orbit that's periodic where the RBRS are going to be different for the same backwards time step due to the time-varying dynamics. The light red polytopes are the RBRS for a given final time, as shown by this terminal set at 4 different points along the orbit. And so taking the union of all of the RBRSI for various final times results in a conservative over-approximation of the unsafe region, as seen by this equation. In this case, the equation represents the unsafe region across the entire orbit. We've essentially swept the terminal set around and computed the RBRSI for every final time or target position. And as such, we can maintain safety across the entire orbit by remaining outside of these states, or sets rather. We can also do this for a subset of the target orbit, since most likely the terminal rendezvous phase will be done in less than an orbital period. So the amount of time steps you go backwards and the amount of target positions one considers are here tunable variables, which are mission dependent. So the goal is to separate the states within some prediction horizon, since we're going to be using MPC, from the unsafe sets that are given by the union of RBRSI. So we clearly have a non-convex constraint where we require that the state is outside of a union of 6-dimensional polytopes. So the union of these polytopes is given or sort of shown or illustrated by these gray polytopes on the right. We've just added a predicted trajectory where we have an initial condition and some future state at some index j. And what we can do is we can use polyhedral inclusion to obtain a half space that's actually a superset of a subset of those unsafe polytopes. So this actually requires solving a linear program. And what you end up obtaining is a polyhedron, or rather a half space, that is a superset of, like I just said, L polytopes that are contained within the union of RBRSI. Then by flipping that half space constraint, we can basically convexify the safety constraint that enables the chaser to remain safe throughout the prediction horizon. We illustrate this here by letting L equal to 2, so we're only looking at 2 nearby polytopes within the unsafe union, and then we construct that half space, and therefore we obtain the vector A naught in this case for the initial time, and then we flip the half space constraint and ensure that the initial condition in this case remains on the right side of that. And we can do that for a step in the future as well, j. And so you want to do this for every single time step in the prediction horizon. We develop an MPC control policy that is onboard implementable and fully autonomous, and to avoid solving non-convex optimization problems, we locally convexified the safety constraints. This technique is well understood, and obtaining a QP is particularly important for spacecraft applications since there are limited computational resources on board. So here we show the cost function and the constraints, and we're going to have a penalty on the states and the control as well as any slack variables. We're also going to have a terminal penalty. And G here represents the safety constraint, which has now been convexified to be of the following form. And the control set U will either be the nominal control set or the failure mode control before and after a failure has actually occurred in our simulations. And naturally, as you solve this optimization problem, you get your optimal control and you apply the initial control step and you repeat. And then just to summarize that our control model is LTV, but in our simulation, we're actually using the nonlinear relative equations of motion. So here we showed some results of this working in practice. We consider a situation where we want to approach the target in a way that is safe if thruster 1 were to fail, given by the red circle on the bottom left. The safe controller uses the safety constraints before and after the failure event. Contrastingly, the unsafe controller uses no safety constraints until the failure event. In these sims, the state at the failure time for this controller is inside the unsafe sets. We allow the spacecraft to then attempt an abort. Naturally, the safe controller performs as designed. By adjusting the trajectory before the failure event, abort is possible as we remain in the safe state space. The unsafe controller, however, enters the unsafe region and thus cannot avoid collision, as seen here. Here we consider a more extreme case where we want to approach the target in a way that is safe if thrusters 2 through 8 were to fail, given by the red circles on the bottom left. We see the same results here, but for an alternative scenario. In this slide, we show the method working for various initial conditions. However, we let the failure time occur at the very beginning. On the left, we see that for all safe initial conditions, a safe abort exists, as no trajectories enter the terminal polytope. On the right, we sampled unsafe initial conditions but used the safety constraints. We show that no successful abort maneuvers exist, and as such, every trajectory enters the terminal polytope. So in conclusion, we characterized the abort unsafe states using robust reachability theory. We demonstrated the existence of abort maneuvers outside of the unsafe sets. And we formulated these convex safety constraints via the polyhedral inclusion. And then finally, we developed an online and fail-safe control policy that in the event of thruster failures prevents the chaser from colliding with a rendezvous target. Thank you very much for your time, and please feel free to reach out to me if you have any questions. I'll hope to answer them in the live Q&A.